All right, today we are going to talk about the length of a line segment, or the distance between 2 points. They really are fundamentally the same thing when we are looking at points on a coordinate grid. Because if we connect those 2 points with a line segment, we will be able to determine the length of the line segment. So why don't we start by creating a coordinate grid. So, oh, that's not a very good one. Sorry about that. I'm going to try that again. There we go. So that is the y-axis, and then I'll come across here for the x-axis, and I'm going to create a scale where each line represents 1 unit. So there's 2 and 4 and -2, -4 and -2. So why don't we start off by actually adding in 2 points. So I'm going to start with the point 1, 4. So this is A, point A, 1, 4. And then this is point B, which is 5, 1. And so we have these 2 points on the coordinate grid, and what we can do is we can calculate the distance of those 2 points, or what we can do is if we connect those 2 points, we have created a line segment, so we could calculate the length of the line segment. How we're going to start off doing this is by actually using some of the strategies or ways that you know from previous math courses. And how I'm going to go about that is, if we look here, I can, using my coordinate grid, I can create a right triangle. If I extend from point A straight down, and I'm actually going to label this as point C, and then if I go from point C straight across, I can go to point B, and I've created a right triangle. And if I label my sides, this will be side C, this will be side A, and this will be side B. So if I have a right triangle, we have learned, that you can use the Pythagorean theorem to determine the length of an unknown side if you know the length of the other 2 sides. In the case here, because we are using a coordinate grid and we know that each square represents 1 unit, we can actually count the squares to figure out what the length of side A and side B are. So starting with B, I'm going to use a different color here. Let's go with purple. So starting from point A, I come down and I go 1, 2, 3, and I know that the length of side B is equal to 3. And then starting from C, I go across to B, I go 1, 2, 3, 4. I know the length of side A is 4. And then I can use the Pythagorean theorem to calculate the length of side C. So A squared plus B squared equals C squared. That means, oops, whoopsie, sorry about that. I'll just erase that and start again. And again, A squared plus B squared equals C squared. So we have 4 squared plus 3 squared equals C squared. Then I have 16 plus 9 is equal to C squared. 25 equals C squared. We take the square root of both sides, and I have 5 is equal to C. So therefore I know the length of my line segment AB is 5 units, or the distance between points A and B is 5 units. Now, this process works really, really well when we are dealing with points that are relatively close or can easily be drawn on a coordinate grid. but it doesn't always work for ones when we have larger numbers or points that are farther apart. So what I'd like to do is to start generalizing some of the information that we have here on our example that we've used. So if we know that point A, let's say point A is point 1 and point B is point 2, we can actually label our coordinates for these points accordingly. So I'm just going to go and choose again a different color. So this 1 would be x1, and point A's y-coordinate would be y1, point B x coordinate is x2, and the y-coordinate is y2. Because really what we've done when we calculated the length of side B and the length of side A is we just looked at the differences between the coordinates. For side B, it was the differences in the y-coordinates of each point, and if we look at the length of side A, it was the difference in the x-coordinates. So we have A is equal to difference in x coordinates. So this is x2 minus x1, which is equal to 5 minus 1, which is 4, which is exactly what we had found. And B is the, oh, sorry, having some difficulties writing here, difference in y coordinates which is y2 minus y1, which is 1 minus 4, which is equal to minus 3. And if you squared minus 3, that would give you 9, so it really is the same thing. Alrighty, so what we're going to do is we're going to use another example now, but we're going to use points that are not as easily drawn on the coordinate grid, and we are going to use this concept of the differences in the x-coordinates and the differences in the y-coordinates and still use Pythagorean theorem in order to solve. So I'm just moving. Okay, so I've gotten rid of the coordinate grid here, or the grid system, so we're just working with a blank page. So let's say that point A is 1575 and point B is 2555. So if we're going through that same process of A and B and C, I'm just going to, sorry, switch colors here for a sec. I'm going to label my coordinates for each of my points. So A being point 1, so I have x1 and y1, and B I have x2 and y2. So we said that A was the differences in x's. So A was equal to x2 minus x1, which is 25 minus 15, which is equal to 10. B was my differences in y's. So I have y2 minus y1, which was 55 minus 75, which is negative 20. And then what I'm going to do is I'm going to put those into the Pythagorean theorem, which is a squared plus b squared equals c squared. So I have 10 squared plus 20 squared is equal to c squared. So I have 100 plus 400, which is equal to c squared. So I have 500, and I take the square root of both sides. Whoopsie, it's just a c. It's not a c squared. Which is 22.36 if I round to 2 decimal places. So we found that the distance between those 2 points is 22.36 units, because I haven't defined what the units are. Now if we look here, I have generalized the Pythagorean theorem, and I can actually generalize that even more, where I don't necessarily have to use a and b. I can actually write the Pythagorean theorem in terms of x's and y's. So I am going to go again, or can I scroll up? No. Sorry, I'm new to this software, so I'm trying to figure out what I can do with it. Yeah, let's not do that. Okay, so alrighty, so here's my new page, and again, I have, if I'm going to generalize the Pythagorean theorem, we said that a was x2 minus x1, and I said that b was y2 minus y1. And let's say that c is equal to my distance. So we know that the distance squared is equal to my differences in my x's, all squared, plus my differences in my y's, squared. So what I can do then, if I take the square root of both sides, I can say the distance between 2 points is x2 minus x1 all squared plus y2 minus y1 all squared. Now often students say, does it matter which point we choose as x1 or x2? And no, it doesn't matter as long as you're consistent. So if you're saying that point A is 0.1 and point B is 0.2, then make sure that you consistently use those. Use the coordinates from point A as 1 and the coordinates from B as 2. If you get them reversed, then your numbers aren't going to work. So this is the distance formula. What I'll do is one more example just to make sure that we can use this one. And to be fair, it doesn't really matter what format you use. You can use this distance formula, or if you choose to use Pythagorean theorem, where we have c squared equals a squared plus b squared, and have that defined by, what a is defined by is x2 minus x1, and b is defined by y2 minus y1, that's completely acceptable. But I just wanted to show how the distance formula was developed. All right, so one more example. All right, so I'm back to my grid background, but I'm not really going to use it. So let's point, and we don't really have to use point A and point B. We could have point M, which is, let's use some negative numbers this time, -4, -12, and N, which is 720. And let's calculate the distance between these 2 points. So we found that the distance is equal to the square root of x2 minus x1 all squared plus y2 minus y1 all squared. And then what I'm going to do, just to make sure, I'm going to label. I always label my points or my coordinates in my point because I am famous for making mistakes and confusing things. So I say, okay, well, this will be x1 and this will be y1, and this is x2 and this is y2. Alrighty, so substituting in, we have distance is equal to the square root of 7 minus 4 all squared plus 20 minus 12 all squared, and I have to make sure that I extend my square root sign along so I don't make mistakes later on. So then I have 7 minus 4, which is 11. We're going to square that. And then I have 20 minus 12, which is 32. So I have 32 all squared. So then I have 121 plus and 32 squared. I'm just getting my calculator out here. So 32 squared is 1,024. So I'm going to add 121 and 1,024, and I get 1,145. And I take the square root of that number and I round it to 2 decimal places. I have 33.84. Just in terms of some terminology here, I just want to let you know that this here is an exact number because it has not lost any precision. If we look here, this is an approximate because we rounded to 2 decimal places. Alrighty, so now you've seen how the distance formula was developed. We've gone through a few examples, so now you should be ready to use the distance formula on your own.